Hey guys, welcome back to General Chemistry Lectures. In this lecture, we're going to talk about atomic structure. So getting to know atoms even a little bit better, how we can identify them. And then we're going to talk about neutrons, so varying the neutrons in something called an isotope. So up until this point, we have talked about the atom. It looks like this. So we've got our nucleus in the middle. We've got this sphere of empty space, and we've got these electrons kind of scattered throughout. So if we look at an atom and start to really understand what it is, an atom could be explained like this. So if an atom was expanded to the size of a football field, the nucleus would be the size of a single blueberry on the 50-yard line of that football field. So when we talk about the magnitude of empty space around that atom, it's a pretty significant magnitude. And if all atoms are composed of the same subatomic particles, so every single atom has protons, every single atom has neutrons, every single atom has electrons, what makes atoms of one element different from another? How do we differentiate aluminum versus carbon? What's the difference? And the answer is this. It's the number of protons. So the number of protons is going to define a particular atom or element. So for example, helium. A helium atom has 2 protons in its nucleus. This is different than a carbon. Carbon atom is going to have 6 protons in its nucleus. So the number of protons is going to be what defines a particular element. Periodic table. So at this point, I'm going to start talking about a periodic table. I highly recommend that you find a periodic table or print out or have a periodic table close to you during this lecture and all of the lectures following. And I also suggest that you always have one with you as you're working through your homework. There are things, some instructors that teach you to memorize things in chemistry. I don't think it's necessarily helpful to memorize a periodic table. That's just not something that I would waste my brain space on. But I am going to teach you how to use a periodic table as a cheat sheet. So for my face-to-face classes, you get a periodic table. You get a literal cheat sheet on every exam. And I will teach you how to use that cheat sheet. So the number of protons defines a particular element. This is also called the atomic number. The atomic number will always be on the periodic table at the top of each element's box. It could be on the top left. It could be on the top right. It could be on the top center, depending on your table, but it'll always be the number at the top. Okay. So here we see helium. So here's the chemical symbol for helium. And then the number at the top is the atomic number, and it also is the number of protons. Those two things are the same. The next thing you'll see on every periodic table is a chemical symbol. So this chemical symbol is going to be a 1 or 2 letter symbol telling us what element it is that we are dealing with. These symbols are, for us lazy chemists, so we don't like to write anything out in full. So we will use chemical symbols moving forward as opposed to writing the whole word out. And then what you will see on the bottom of each box on a periodic table is the atomic mass of an element. I like to call this the average atomic mass. This is going to be a number that we calculate shortly, but it is the atomic mass or the average atomic mass for that particular element. So how do we get this atomic mass? Why am I calling it an average atomic mass? Well, it's an average of something called isotopes. So let's look at an isotope. So here we've got an experiment. So let me talk to you about this experiment and how isotopes were discovered. So here we have a positive cathode ray tube. So what you need to know is there's a stream of gas, neon gas in this case, that is going through a focusing device. We are then going to bend this stream of neon gas around a corner, and we're going to see what kinds of things we detect over here. The important thing to remember, it is a stream of neon gas going in, and it is a stream of neon gas that is going to hit our detector. It is the same element that we started with that hits our detector at the end, so nothing changes there. So that being said, if neon gas is going in and neon gas is coming out, that must mean the number of protons will be the same. That's not going to change. Keep that in your mind. All right, so here's what's going on. Our stream of neon gas is coming towards our curve, so focusing device curve. We introduce some sort of magnetic or electric field to make that stream of gas turn around the corner. And what we found is that instead of one stream of neon gas going around the corner and one stream of neon gas hitting the detector, we actually found 3 streams hit the detector. So the first one went around the corner very speedily. So it took a nice sharp turn around that corner and boom, it was the first one to hit our detector. So we could think of that like a motorcycle going around a curve. It takes a really short path and it hits the detector first. The next one took a little bit longer of a path. So not as sharp as our motorcycle. So we could think of this as like a car. So still pretty sharp angle, but not quite as sharp as a motorcycle. Boom, it hit the detector. Then the last thing that we saw is this stream of gas that took a nice wide turn around the corner, and it hit the detector last. So we could think semi-truck around the corner. Okay, so we've got small, fast, hit the detector first. Medium, slow, hit the detector second. Big curve, really slow, hit the detector third. What's the difference in those 3? All of them are neon, so they all have the same number of protons, but they have a different mass. It got bigger and bigger, which caused the curve to be wider and wider. So if the number of protons is the same, what subatomic particle must be different for all 3 of those? The answer is neutrons. So an isotope is an atom that contains the same number of protons, always neon in this case, but varies in the number of neutrons. So isotopes are going to have slightly different masses. Remember that neutrons do have a mass. So if I add an extra neutron, the mass is going to go up. If I take away a neutron, the mass is going to go down. So here we see 3 isotopes for neon. The first one had a mass of roughly 20 AMUs. The second one had a mass of roughly 21 AMUs. And the third one had a mass of roughly 22 AMUs. So we see that as we added neutrons, the mass went up. There's going to be a couple different ways that we symbolically represent isotopes. So it's a couple different ways that you will see this material presented, and I will assess you on the material. The first one, actually, I'll show you the second one first. So let's talk about this one. This might be one way that we symbolically represent an isotope. So what you will see in this case is you will see a chemical symbol. So if I were to apply this to the example we've been talking about, the chemical symbol might be neon. Ne. So that's our chemical symbol. The number in this case on the bottom will be the atomic number or the number of protons. So I look at my periodic table. I find neon. It's the 10th element. So I know that neon has 10 protons. Its atomic number is 10. The number on the top is going to be the mass number. I'm going to pick an isotope for you just for demonstration purposes. But the number that I write up here would be the mass number. The mass number is the number of protons plus the number of neutrons. So we're adding together the two particles that have a mass. So protons plus neutrons. Okay. So I can actually determine the number of neutrons this isotope has with the information that's given. If the mass number is protons plus neutrons, and the atomic number is the number of protons, I can subtract these two numbers, and that tells me that this isotope has 10 neutrons. See that? Okay. So that's one way that we symbolically represent them. We use this chemical symbol, mass number over atomic number. The other way that we symbolically represent them is how you see it on this slide. So I could write Ne21, or I could write out the word neon 21. In this case, that 21 is the mass number. I'm telling you what the mass number is. Okay. From this information, from what you see on the screen, I could then write the other symbol. So then I could write the Ne. It's still neon, so it still has 10 protons. And in this case, the mass number is 21. Okay. Lots of different ways that I can ask you about this material. I could give you the chemical symbol, and then ask how many neutrons. I could give you this, and I could ask how many neutrons. I could ask the atomic number. I could ask you to write the other symbol. I could give you this and just have an X right here. And I could say, well, what element am I talking about? And you'd have to be able to identify that particular element. So lots of different ways that this material can be assessed. So make sure you have a solid understanding of all of it. Okay. All right. So why did we just take this kind of detour through isotopes if I was originally talking about average atomic mass, right? So it turns out that the number on the bottom of the periodic table, the average atomic mass, is in fact an average of all of the isotopes that exist. So in this case, neon 20, neon 21, and neon 22 all exist in real life. So to get the average atomic mass, I'm going to take an average of those three isotopes. But if I were to add up these three numbers, and divide by 3, it doesn't equal this number on the bottom of the periodic table. It actually equals 20.99. So the average atomic mass isn't just a quick add and divide. The average atomic mass is actually a result of what we call a weighted average. So there's not equal amounts of these isotopes that exist in real life. We've got more of one kind than of another. So we have to take a weighted average. So the average atomic mass that you see on the bottom of a periodic table is the average of the mass of the isotopes and something called their natural abundance. The natural abundance is going to be information that has to be given to you. It's not something that you're going to know. So I'll have to present it, or an instructor will have to present it to you. So here's an example of the natural abundance. So what this tells me is that if I had a container of neon gas, I had a container sitting on my desk, I reach in and I pull out one atom. 90% of the time, that atom is going to be neon 20, the isotope neon 20. Reach in, pull another one out. 9% of the time, that's going to be neon 22. Reach in, pull one out. 0.26% of the time, it's going to be neon 21. So all three of these isotopes exist in real life, but they don't all exist in the same amounts. Neon 20, for whatever reason, is the most stable, so that's the highest percentage. And neon 21, for whatever reason, is the least stable. And we see that only 0.26% of the time. Okay. So how do we get to the average atomic mass? So the next slide I'm going to depict for you shows a formula. I think this formula makes it a lot more difficult than it needs to be. But essentially what we're going to do is we're going to take the mass of a particular isotope and we are going to multiply it by the natural abundance and we'll get a number. And we'll do that for all three. Then we just simply add those numbers together. That's it. That's all we do. One thing to note, though, is a percentage. We don't typically multiply by percentages, so we want to make sure that we put that back in its decimal form. So to put 90% into a decimal form, remember that is 90 over 100, or the decimal would be 0.9. So we're moving this decimal over 2 places each time. Okay, that's what we're going to be doing. So like I said, here's the formula that the textbook has. The fraction of the isotope, so that's going to be that decimal times the mass of the isotope. And you're going to do that for each of these and add them together. So let's do that. And I think I'm going to go back to this slide. I'm going to do it on this slide with you guys. I like this slide. Okay. So pull out my calculator here. I'm going to take the mass of the first isotope and I'm going to multiply it by the decimal. So 0.904838. Okay, so 0.9924 times 0.904838. And we get 18.08. 9, 8, if you will. So the pause there, I was trying to determine number of sig figs. So even though we are moving on to a new topic, a new chapter, we still do need to consider significant figures. Both of these numbers had 6 sig figs, so that's what I was trying to do quickly. Here we're going to see 4, and here we're going to see 5 sig figs. All right, so I'm going to do the same thing. I'm going to take the mass of the next isotope and multiply it by the percentage. So moving this decimal over 2 places, it's actually 0.002696. So 20.9940 times 0.002696. And we get 0.05659. Okay. All right, lastly, I'm going to take 21.9914 times 0.09. So 21.9914 times 0.092465. And I get 2.0334. All right, now that we've gotten to this step, what we're going to do is simply add these numbers together. We're not going to divide by 3. We're not going to do anything wonky like that. We just simply add them together. So I'm going to take 18.0898 plus 0.05659 plus 2.0334. And we get 20.17979. Let me quickly consider significant figures. So this one had 4 decimal places, 4 and 4, not lined up at all. So we had 4 decimal places. So 1, 2, 3, 4. We'll cut it off right there. So that would be our answer. 20.1797 AMU, or atomic mass units. Cool thing about these is you already have the answer. So your answer key is the periodic table. So if I were to go to the periodic table and I were to look at the average atomic mass of neon, the number on the bottom, the particular table that I am looking at says 180. Yeah, that's pretty doggone close, right? So average atomic mass, we're going to take the mass of the isotope times the natural abundance, but make sure we make that natural abundance a percentage. Do that for each isotope available. Then we're going to add those numbers together. I hope you guys found this helpful.